So today what we're going to be doing is looking at further applications of the concept of slope. We're going to be looking at the difference between an average rate of change and an instantaneous rate of change. And most rates of change are measured with respect to time. In other words, the rate at which I eat chicken wings on Friday night might be 5 chicken wings per minute. It wouldn't be. But the units would be chicken wings per minute. It might be 20 chicken wings per hour. Maybe that's more appropriate. The rate at which I spend money might be so many dollars per day. The rate at which a plant grows might be so many centimeters per week. But not all rates of change need to be measured with respect to time. Many are, but they don't have to be. The bottom line is, graphically speaking, when we talk about a rate of change, it's y with respect to x. So yes, if I have a graph with chicken wings on the vertical axis and hours on the horizontal axis, then the slope or the rate of change will be chicken wings per hour. But it doesn't have to be that time is on the horizontal axis. And I'm not suggesting time is on the vertical. I'm saying maybe one of the variables isn't even time. Let's keep that in mind. There's a difference between an average rate of change and an instantaneous rate of change, and I can cut to the chase right now. Graphically speaking, an average rate of change turns out to be the slope of a secant line between 2 points without regard to anything in between. We have no idea what happens in between. If we just take those 2 points and we find the slope between them, what we will be doing is finding an average rate of change of y with respect to x. On the other hand, an instantaneous rate of change, and if you've taken physics, you might have a better understanding of the word instantaneous here. The instantaneous rate of change is the slope of a tangent. So if I have a graph and I have a point on the function and I find the slope of the tangent, what I'm finding is the rate at which y is changing relative to x at that instant in time, not over a time interval or not over an x interval, but at a specific value of x. And we're going to start off with an example that is a physics problem. But you need to understand, and I'm just going to speak to everybody here, whether you've taken physics 20 or 30 or not. I think it's probably the case that all of you have. But you cannot solve problems in a calculus class dealing with motion using the kinematics formulas. It's not entirely true. We could solve this one using the kinematics formulas, but you cannot solve this problem using kinematics formulas. And I wonder if I have another one here. I just want to see. Yeah. You cannot solve this problem using the kinematics formulas. And if you're interested, I hate to just leave it hanging there, so I'll give you the reason for this. Those kinematics formulas, and I think everybody is aware of what I'm talking about, things like d equals vit plus a half at squared, or vf squared equals vi squared plus 2ad. Those kinematics formulas you learn about in physics 20 are only useful if the acceleration is constant. And in calculus, we don't limit ourselves to constant accelerations. The acceleration could be changing. In other words, the acceleration might depend on time. It might not, but it might depend on time. So bottom line here is we do not want to rely on kinematics formulas to solve these problems. So let's take a look at the first one. When a ball is dropped from a CN tower in Toronto, the distance that it falls, measured in meters, is a function of time, and it's given by s of t equals 4.9 t squared. So first of all, s is what we use for distance in math. We're just going to have to get over that fact, okay? S is distance or position. We do not use d. D has a special place in the math world at this level. So what we're saying is s of t is the distance. I know you should understand function notation, but I want to explain this to you just on the off chance that you're lost by it. S of t is the distance after t seconds. Okay. listen, if you don't like that s of t, there's nothing to prevent you from doing this. There's nothing to prevent you from just saying the distance that it falls is equal to 4.9 t squared. But the function notation can be useful at times. So that's the formula for the distance or position. Listen, we don't really get into a big twist today about the difference between position or distance or displacement. It's all the same today. Okay? We'll worry about more complicated things later. Find the average speed of the ball from t equals 2 to t equals 6 seconds. Well, when you find an average speed, what you are doing, and I am lucky because I think everybody in this class has taken physics. I'm confident of that. So, we are going to kind of maybe introduce the idea here, just to get us going, that in physics we say average speed. I'm not going to write the variables here, is the change in the position divided by the change in the time. And I've always hated the change in time. It doesn't sit right with me. Why don't we just say time? But anyway, that's actually a formula on your physics formula sheet. So the bottom line here is if we take a look at this graph of s as a function of time, it's not that difficult to see that this will be a parabola. It's 4.9x squared. It's a parabola with some kind of vertical stretch factor. But the bottom line is the parabola will look like this. I'm hesitant in putting an arrow on the end of that line because obviously the ball is going to hit the pavement sooner or later. It's not going to continue to fall and travel further and further and further. But here's my point, that there is a point here where the time is 2 seconds, and this t brackets s is not t as a function of s. S is the units of seconds. And there is also a point over here at 6 seconds. When you are finding an average speed, using this red formula, which is a physics definition, what you are doing is you are going to subtract whatever this is, which will be s of 6, and you are going to subtract from that whatever this is, which will be s of 2, and that will be your change in position, your final position minus your initial position. And none of this should be mind-blowing to you. But your change in time will be the 6 seconds minus the 2 seconds. So if we write that out, our average speed will be s of 6 minus s of 2 over 6 minus 2. But that's rise over run. Right? Delta position is the change in y. So what you're really doing, and you can choose to draw in this line or not, quite frankly, doesn't matter. But what you're really doing to find an average rate of change is you're just finding the slope of a secant line, the slope of a line that connects 2 points. So what we're going to have here will be, for the answer to the question, we're going to have to calculate 4.9 times 6 squared minus 4.9 times 2 squared. And I know, particularly if you're in my Math 30 class, I made a big deal this morning about making sure you put substitution in its own set of brackets. I don't think at this level we need to put the 2 in its own set of brackets and then square it outside. We know 2 squared is 2 squared, 6 squared is 6 squared. And then on the bottom we have 6 minus 2. And there's a nice kind of symmetry to what we've written here. And I want to point out to you that if you factored 4.9 out, and we have no reason to, we're not going to, but if you did, you'd get a difference of squares, which would factor, and one of the factors of the difference of squares would be 6 minus 2. That's important for later. So we just run this through the calculator, and I'm not going to worry about exact values for this. I'm calculating it by factoring the 4.9 out and then just multiplying by 36 minus 4, which is 6 squared minus 4, 2 squared. and then I divide by 4. Anyway, I'm getting 39.2, and I'll give everybody an opportunity here to confirm that. I'm pretty sure that's right. As weird as it sounds, I remember that number from previous times I've taught this lesson. $39.2 is right, correct? Okay, and you take a look at the units of what we did. Our rate of change was measuring position divided by time, so we're getting 39.2 meters per second. And that's an average rate of change. Does that mean, I mean, you can look at the graph and know that it doesn't mean this, but if somebody came into the room and all they saw was 39.2 meters per second, and let's even imagine that it's a grade 9 student, and you ask the grade 9 student, what does that mean? Most likely the grade 9 student will say, well, the object was traveling at a speed of 39.2 meters per second. And I might ask the grade 9 student, what do you mean by that? Well, that's how fast the object was moving. The fact of the matter is, since this is an average rate of change, since this was an average rate of change, there's no guarantee that it was traveling at that speed for any real length of time. There is a guarantee, and this is a theorem in calculus, that there must be some point in between where it's traveling that speed. And I'm getting a little off topic here, but this is something called the intermediate value theorem that we will talk about most likely later in the semester. The fact of the matter is the slope of this line represents a speed of 39.2. There's a theorem that says if the slope of the secant is 39.2, there must be some point in between that has that slope, which kind of makes sense visually. It doesn't have to be halfway in between, although it probably is in this case. It doesn't have to be. Any questions with A? All right, B. Find the instantaneous speed of the ball at 3 seconds. Well, what we are trying to do is determine the slope of the tangent to this function at 3 seconds. So I'll just quickly redraw this. So we have this function, which is s of t as a function of t. And what we're after now is not a speed between 2 points in time. We're interested in a speed at a particular point in time. So I hope I've been successful in getting you to understand up to this point. We're talking here about its tangent slope, okay? So what we are after is the slope of the tangent to this point. And, you know, the diagrams are here to aid in my explanation. They're not something that you need as part of your solution. What we have in the past done is we have said, let's take some other point and call it Q. And this concept should not be unfamiliar to you, okay? And don't write down anything else until I say. This other point Q, we have sometimes called this x plus a, where this is a, right? And x, actually what we've done is we've called that x, and we've called that a, and we've said as x approaches a, the slope of the secant approaches our answer, right? But what we've done instead of doing that is we've said, well, let's call this a, and this a plus h. And if you use these two, then your limit, and I'm not saying don't write this down. If you want to write it down, you can. But I'd rather you just focus on my words and what we're looking at. Then your limit for the slope of the tangent will be the limit as x approaches a of the slope of the secant, right? Should make sense to you, I hope. On the other hand, if you chose to take this tact, where you're going to call 3a and this x coordinate of q a plus h, then what you are doing is you're going to be using the following to find the slope of the tangent. It's going to be the limit as h approaches 0 of the slope of the secant. And it doesn't matter, we do calculate the slope of the secant in a particular way for the yellow highlight. It would be f of x minus f of a over x minus a. For the blue, it would be f of a plus h minus f of a all over h. Okay? But for some reason, and I can't find the origin of this reason, but whenever we deal with instantaneous rates of change, we like to call this x1 and this x2. All that's going to happen here is our slope of the tangent, which is the answer to this question, and now you can start writing, will be a limit as x2 approaches x1. It's like somebody's come up with a third formula, but you know what? This is pretty much the x approaching a formula, except we're not calling that value of x that's 3. We're not calling it a, we're calling it x1. And it will be of the slope of the secant, which will give us this. The slope of the tangent, the instantaneous rate of change of y with respect to x, will be the limit as x2 approaches x1 of the rise, which will be that. And I can add a little bit more to this diagram if you like. And part of successfully doing math at this level is being able to construct diagrams as part of your solution. So if I call this 3x1, then this is f of x1. I hope you've become really accustomed to that idea, that whatever the x coordinate is, the y coordinate is f of that x coordinate. And this is f of x2. So you can see by looking at the diagram, I mean, I could draw in a triangle, but I don't think it's necessary. The rise is f of x2 minus f of x1. The run is x2 minus x1. And I hope it's not lost on you that this is the limit as x2 approaches x1 to find the instantaneous rate of change, but, and I really don't think you should highlight or do anything here, but this is what we're using for the average rate of change. That's what we're using for the previous one. And I know that there's probably somebody out there who would look at what I just wrote and say, well, you've made a mistake. And perhaps you could nitpick and say, I have made a mistake. This is actually S of T2 and S of T1, and this is actually T1 and T2. But I'm trying to teach this to you in the general sense. Okay? So, what does this general, get rid of this. What does this general statement that I've explained and derived, this, tell us in this question? It tells us that the velocity at 3 seconds is equal to the limit as x2 approaches x1. Well, I better be more specific here. T2 approaches T1 of S of T2 minus S of T1 over T2 minus T1. And T1 is going to be 3. And my goal in using this notation and this notation is that your written work and your understanding of the language of math becomes more sophisticated. And you know this already. If you look at some of the work you've done last week, and if you were to go back in time a month ago and look at that work, you wouldn't know that it was your work. That's how much you've evolved as a math person. It continues to evolve. So what's going to happen here is this basically becomes v at 3 seconds will be equal to the limit as t approaches 3 of s of t minus s of 3 over t minus 3. And I don't always point this out, and sometimes people don't even realize it. But this is the x approaching a formula, right? That's what's going on here. All this stuff with x1 and x2 and t1 and t2 and all that is just a general idea here that you need to get in your brain so that you can build this limit to answer the question. So now we're going to answer the question. This is the limit as t approaches 3. I better just make sure. It is 3 seconds, isn't it? Of what is s of t? Well, this is why I don't necessarily like just dropping the function notation, because you can't get away from it here. S of t is 4.9 t squared minus s of 3. So how do you find s of 3? You put 3 in for t, but we don't want to calculate it. We do not want to calculate what 4.9 times 3 squared is. How many of you is it clear why we are not interested in what 4.9 times 3 squared is? Why do we want to leave it that way, Jay?
Because we need to cancel the bottom.
Right, we can factor the 4.9 out, we get a difference of squares, we factor it. We know this limit has to exist because the object has a certain speed at 3 seconds, right? So we know since, and I guess we didn't really say this, but let's get out with it. When you put 3 in, you get 0 over 0, right? So we're going to simplify this. We're just evaluating a limit, which you've had tons of practice doing. Take the 4.9 out. If I were doing this on my own, I'll just write 9. If I were doing it on my own, I probably would have written on the top 4.9 times t plus 3 times t minus 3. I don't think that's a big leap in complexity in that line. So this is the limit as t approaches 3 of 4.9 times t plus 3 times t minus 3. Cancel those. Bob's your uncle. I don't know what that means. It's an expression. I guess it just means we're ready to go. And now I can put in 3 for t. And this is where you drop the limit. So we end up with 6 times 4.9. I want to say it's 29.4. It's 29.4 meters per second. Any questions with, well, and just to top this off, it just means that at that instant in time, that's the speed. It's traveling a little bit slower immediately before, a little bit faster immediately after. Any questions with B? So just to summarize this, and I think I've kind of laid the framework for what's going on here. An average rate of change of y with respect to x from one point of a function to another point of a function, we call the points x1, f of x1, and x2, f of x2, is delta y over delta x, which is delta f of x over delta x, which is f of x2 minus f of x1 over x2 minus x1, which is the secant slope, right? So an average rate, we shouldn't need to look at a graph all the time to reason it out. An average rate of change is the slope of a secant from point to point. Whereas instantaneous rate of change at a particular point is the limit as the run gets to be 0. And now we're encroaching on something that we'll talk about tomorrow. That when you find the slope of a secant, it doesn't matter whether h approaches 0 or x approaches a or x2 approaches x1, the run is getting smaller and smaller while one end stays fixed. So it's the limit as delta x approaches 0 of delta f of x over delta x, which is the limit as x2 approaches x1. That's the only way delta x can become 0 or closer to 0, of f of x2 minus f of x1 over x2 minus x1, and that's the tangent slope. None of these formulas are given to you for exams. And quite frankly, I think if you have a really good understanding of what's going on here, you shouldn't need a formula. You should just be saying, I'm finding a slope of a secant or I'm finding a slope of a tangent. So example 1, that first part was just a warm-up. Or, help me out, did it say example 1? Do I have to change my notes or did it say warm-up? Warm-up, okay. The displacement of an object is given by s of t, so I could have said position, equals 2t squared minus t. What is the average rate of change from t equals 2 to t equals 5? And also determine the instantaneous rate of change at 3. So let's first of all start talking about the average, well, average speed. We do use v for speed. We don't make a big deal about vector symbols when we get to velocity, but we'll worry about that later anyway, it doesn't matter. This will be s of t2 minus s of t1 over t2 minus t1. Which in this particular case is going to become s of 5 minus s of 2 over t2 minus t1. Oh, sorry, over 5 minus 2. I hope it's clear that this thing we're calculating will be numerical everywhere. There will be no t's. It's not a limit, it's just an expression. So there is nothing wrong, in fact I would probably encourage it, in calculating the position at each of these points. And all we're doing is we're taking 2 and putting it in for t in that function at the top of the screen. So 2 times 2 squared minus 2 will give, I believe, 6, but you guys have to keep me on my toes here. So I'm putting 2 in for t into s of t equals 2t squared minus t. When I put 5 in, I believe I get 45. But again, I'd like some feedback here in terms of whether those numbers are right or not. They appear right. So what will this be? It will be s of 5, which is 45 meters, minus s of 2, which is 6, over 5 minus 2, which is 3. You know, and if this were maybe a physics class, we'd be putting meters and seconds. We just throw it in at the end. By my count, that's 39 over 3, which is 13, but you can double check. Okay, so it's 13 meters per second. So that's the average speed from the 2-second to the 5-second mark. We are also asked to find the instantaneous speed at 3 seconds. So for the second part, v at t equals 3 will be a limit, and I have to teach you the t2 minus t1 thing. I have to. But whenever it comes to an instantaneous rate of change, I just fall back on the x approaching a approach, or t approaching a. So this will be the limit as t approaches 3 of s of t minus s of 3 over t minus 3. And again, I'm coming to this thing that really, I find it spooky. It kind of blows me away a little bit. We're going to put the function in for s of t, and we're going to figure out what the function is at 3. And what we are going to get all the time in the numerator is something that is factorable. And one of the factors has to be what's in the denominator. To me, that's spooky. And I mean, I understand the mechanism by which it happens. But it's still, Doesn't keep me up at night, but it bothers me a little bit. Okay, and I'll show you an example with decimals that illustrates the point in a minute. So this is the limit as t approaches 3 of, I think it was 2t squared minus t, wasn't it? Well, let's figure out what s of 3 is. I want to say you get 15. Don't let me just do the math. You work it out as well. That's 15. So this becomes minus 15. And what I'm telling you is that this is always factorable. In fact, if you have faith in the math and faith in your skills, you shouldn't even need to use trial and error here. You should say one of the factors must be t minus 3. The other factor has to start with a 2t because I need to get 2t squared, and it must be plus 5 because I need to get negative 15 as a product. And I'll pause for a second and allow you to FOIL that out and convince yourself that it would be factored correctly. And again, the factors cancel. Now we can put 3 in for t and get 2 times 3 plus 5. Is that 11 meters per second? You know, I just want to show something to you briefly here. So we're done with that example. Does anybody have any questions with that one? Imagine it said this, that s of t is equal to 1.95 t squared minus 0.8 t plus 1. Okay? And I want to find the instantaneous speed at t equals, I don't know, it doesn't matter, 2 seconds. This is going to become the limit as t approaches 2 of 1.95 t squared minus 0.8 t plus 1 minus whatever s of 2 is. And I would like everybody to calculate s of 2. So you're going to take 1.95 times 2 squared minus 0.8 times 2 plus 1. I'm going to do the same thing. It's easier to confirm by looking at nods of the head than asking people to tell me what they got. So 1.95 times 4, that's 2 squared, minus 0.8 times 2 plus 1. Did anybody else get 7.2? Okay, so it's minus 7.2. And this is over t minus 2. And we can condense this 1 minus 7.2 and write it as negative 6.2. You with me? So imagine you had no idea about limits and what's going on, and I tell you, you have to simplify that expression. You're going to do something silly that you're told to do in Math 20, which is to maybe multiply the top and the bottom of this by 100 to remove the decimals from all of that stuff on the top. But the fact of the matter is, there has to be a factor of t minus 2 on the top. There has to be. Which means this has to be plus 3.1, because 3.1 times 2 gives you 6.2. And this has to be 1.95 t. And FOIL that out, you're going to get what's on the top. I guarantee it. We don't have to. But to me, that's weird. Anyway, let's move on. I'm just going to leave this up on the other screen because I see some of you doing a calculation here. All right, number 2, a balloon is being blown up at a constant rate. Determine the average rate of change of the volume of the sphere with respect to the radius. This is not about time. Okay, we're adding air to the balloon at a constant rate. What this is saying is find delta volume over delta R from R equals 10 to 14. You do not need to draw this. My hope is that when I sketch this, you look at it and go, well, I know that's what it means. Here's R equals 10. Here's R equals 14. Whatever this thing looks like, and it doesn't matter, it's going to look something like that, okay? We'll get to the formula in a second. I'm asking you to find the slope of the secant. That's all I'm asking you to do. This will be V of 14 minus V of 10 over 14 minus 10. So the volume when the radius is 14 minus the volume when the radius is 10 divided by 14 minus 10. Only problem is, what's the function for volume? Well, the volume of a sphere is equal to 4/3 pi r cubed. I'm perfectly aware that most balloons are not exactly spherical, but that's what we're going to go with. It's 4/3 pi r cubed. You will get data sheets, lots of data sheets in this course, and one of the data sheets that you will have will be a geometry data sheet. It'll have formulas for two-dimensional areas or two-dimensional shapes, and also for volumes of 3D objects. So that's the formula we're going to use. So this will be 4/3 pi times 14 cubed minus 4/3 pi times 10 cubed over 14 minus 10. And it's just number crunching time. All right? We don't want an exact value here. I suppose you could have an exact value by factoring the pi out and calculating this whole thing as a fraction and saying it's that number times pi. When the time comes for exact values, we will be able to handle it. I'm just saying, let's crunch the numbers today. $18.26 is what I get. When I calculated it, I factored the 4 pi over 3 out, and I multiplied 4 pi over 3 by 14 cubed minus 10 cubed. And then I divided by 4. So does anybody else get 1826? Okay. Now what are the units of this? I just wanted to see how it rounded. Well, the units are volume units over radius units. And this is going to be the one time, well, the first time for you, where you do not do what you've always been taught to do, which is simplify units. You do not simplify this into square centimeters, because then it loses its meaning. If I say the rate of change of volume with respect to radius, the average rate of change is so many square centimeters, that doesn't make any sense, because this is a unit of area. And this question has nothing to do with area. You leave it this way because you're saying that for every 1 centimeter increase in radius from 10 to 14, on average, the volume went up by 1,826 cubic centimeters. Okay? What if I say, what is the instantaneous rate of change of the volume? I'm hoping at 13 I'm hoping that when you write this down and think about what you've written down, that makes sense. We're back to the x approaching a thing, except it's not x, it's r. It's not a, it's 13. So this will be the limit as r approaches 13 of 4/3 pi times r cubed minus 4/3 pi times 13 cubed. And I hope, and we've encountered this in an earlier example with differences of squares, I hope it's obvious why you do not want to calculate 4/3 pi times 13 cubed. Because if you take that 4/3 pi out, you're left with r cubed minus 13 cubed, which is a difference of cubes. One of the factors of a difference of cubes, in this case, will be r minus 13. I'm going to save us a bit of time here. When I take the 4/3 pi out, I'm left with r cubed minus 13 cubed, which is r minus 13 r squared plus 13r plus 13 squared. Kablam. We're ready to put in 13. And I don't know on what context this came up under, but I'd mentioned this before, that very often when you do calculus with this difference or sum of cubes, these three terms all end up being equal. Like when I put 13 in, I get 13 squared, which is 169. I get 13 times 13, which is 169. And I get another 169. So I'm going to challenge you here to think about why the answer to this question is that. This is 13 plus 13 plus 13, which is 3 times 13. 3 cancels with this 3, and I'm left with 13 on the top times the 4. It's not necessary that you do this, but I'm pointing out there's an interesting coincidence that happens here. Regardless of how you do it, you should be able to get an answer of about 163. And if you do it the long way and you go 4 times pi times 13 times 3 divided by 3, you're going to get that answer. Is 4 times 13 52? Yes. Yeah. So 163-ish centimeters cubed per centimeter. Any questions with that example? All right. Final example. And I'm just, we could probably be done, but I like this example. This is an experimental set of data. A thermometer is taken from a room where the temperature was 20. That should probably say where the temperature was 25. Not probably. It needs to say where the temperature was 25, because the initial temperature when you look at the data says 25. Never noticed that till just now. Yours says 25? Okay. So it's not your problem, it's my problem to fix. And of course, it's no surprise that when you take that thermometer into the colder environment of the outdoors, that the temperature starts to drop. You know, I hope you understand, particularly if you've taken Math 30, that this temperature will continue to drop, but it's going to approach 5. There's going to be a horizontal asymptote at 5 centimeters, because that's the temperature outside. What the question says to begin with is, what's the average rate of change from 1 to 5 seconds? It's not difficult. All we have to do (1 to 5 minutes, I suppose that is). All we have to do is take the change in temperature divided by the change in time. We're using empirical or scientific data here. We're not using a formula to calculate the temperature at those times. We're simply saying that this will be 10.5 degrees Celsius minus 20.4 degrees Celsius over 5 minus 1 minutes. $2.225? 2.475? Okay. And it's negative. Negative 2.475 degrees Celsius per minute. So if you're familiar with the concept of cooling objects, the temperature doesn't go down linearly. The temperature goes down as an exponential function. It's a decreasing exponential function that we talk about in Math 30. So it isn't that there's a slope of the function that's this. That's the average rate of change of the temperature. If I said from 4.4 to 4.5, that is here, from 4 to 4.5. I'll just throw this out. How many of you see whatever we get here for this second question is closer to an instantaneous rate of change than the first answer? Because we're looking at a very tiny interval here. So you're going to have 11.2 minus 12.1 over 4.5 minus 4. See if I can get this one. That's 1.8, negative 1.8, I think. Seeing a nod. Negative 1.8 degrees Celsius per minute. Now, imagine I asked you, and you don't have to imagine very long, all you have to do is look at the final part of this lesson. What is the instantaneous rate of change at a particular time? Well, we don't have a function, but there is a way for you to enter that data into your calculator and get a function. How many of you are taking Physics 30 right now? Okay. Those of you that are taking Physics 30 right now, either in Physics 30, probably not yet, but at some point in high school, have you ever done a linear regression? Does that ring a bell? No, not for everybody who's currently in Physics 30. I hope everybody in my Physics 30 class from last semester or last year knows about a linear regression. Regression is the idea that you can put data into a calculator. There's a way to do it on paper, but man, it's ugly. You put the data into the calculator, tell the calculator to find the equation. Well, if you were to put this data into your calculator, you would discover when you plot it, it looks like that. It's not linear, okay? But you would use all of your vast knowledge of math and say, that's exponential. And if you go to, we're not going to do this, I'm just saying if you wanted to, if you go to your statistics menu and your calculate submenu, you will discover that there is a exponential regression. Okay, and depending on your calculator, you might get slightly different answers. But what I'm telling you here is that a student did this and they got 25 times 0.83 to the t. So if you look up here, there's my data, and if I plot 25 times 0.83 to the t, that's the function. Okay. We're going to use the calculator to find the instantaneous rate of change of the temperature at 3.25 minutes. And it's easy. All we have to do is enter this function into our calculator. 25 times 0.83 n bracket raised to the x. Set up our axes so we see a reasonable representation of the graph. Since this graph goes from t equals 0 to 5, why don't we just do that? 0 to 5 for x. And we have to start up at 25. We have to go from 0 to 25. So in my window settings, I'll go 0 to 5. I was going to say let's go to 6, but we're only interested in 3.25 minutes, so who cares? And let's go from -2 to 26. I do like a bit of cushion room vertically. That way I can see the axis on the bottom. So this is what the graph looks like. Well, I can see the axis on the bottom, but my axes are turned off for some reason. And I think you know how to find the instantaneous rate of change. I've shown this to you, but I may not have called it an instantaneous rate of change. Called it a slope of a tangent. You go to your calculate menu and choose this. Enter in was it 3.25, Alex? It was. So it's negative 2.5 degrees Celsius per minute at that point. There will come a time, it'll be in the next unit, no, it'll be 2 units from now, where you will be able to determine the answer to this question algebraically. If you know that y equals 25 times 0.83 to the t, you will be able to determine a formula for the slope of the tangent anywhere. So a number of applications here. The bottom line is an average rate of change is a slope of a secant between 2 points, if you want to think graphically, and an instantaneous rate of change is a slope of a tangent at a point. Whatever limit formula you want to use, just go for it. I don't care. x2, x1, xa, h, you got at least 3. Although the x2 approaching x1 and the x approaching a are really the same thing.